Yeah, next talk is by Jinfeng Jia, and I'll let you get started.
Yeah, first of all, I would like to thank organizer giving me this chance. Today I will talk a very old topic. It's about topological superconductor. Yeah, first I give a short introduction, then I will review this minor zero mode in this system. Then I will focus on this multiple minor zero mode in one vortex. If I have time, I will talk about segmented Fermi surface. Finally, summary. Topological superconductor is interesting because it hosts minor fermions. Recently, we also called the minor zero mode. Minor zero mode were first proposed by Minor in 1937. Since its simplest non-abelian area can be used for topological quantum computing, so it's a hot topic recently. Actually, in 2002, follow Liang's proposal, we made this TI and superconductor heterostructure, and we found on this TI surface we can see the Dirac-Cohn structure, and also we can using STM we can get this superconductor gap. So this one should be a topological superconductor. So on this surface, we should be able to see minor zero mode. But before that, we have to know some features of this. Something wrong. Of this minor zero mode. One feature is zero energy, and another way is this wave function of minor zero mode is some cone shape. It's not a point. And also minor zero mode has spin, can induce this spin selective angular refraction. So we have to see all of them. We want to claim we see minor zero mode. For the zero energy, we did see a very strong zero-watt peak. And when we apply a small magnetic field, this intensity of the zero-watt peak is strong. But when the magnetic field larger than 0.18 Tesla, the intensity of this zero-watt peak dropped a lot. Actually, for X-wave superconductor or on signal field, this intensity of zero-watt peak then change with magnetic field. So when this intensity is strong, we think they have contribution from minor zero mode. Also, we did a spatial distribution of this zero-watt peak measurement. What we do is like this. At the center of vortex, we only have one peak. Then we move our peak from center to the edge. And we found that this peak become broader and broader. Here, one peak split into two. And if we move further, this splitting become larger and larger. We can redraw this data using this color image, and we use this small radar cross represent the peak position. Then we can use two dot line connect these peaks, and we found that this two dot line meet at the center of vortex. That means this zero-watt peak starts splitting from center of vortex only after distance away. When the splitting is large enough, our STM can resolve this kind of splitting. For one quantum layer, 2 and 3 quantum layer field, same situation. But from 4 quantum layer field, the situation changes. you can see the 2.9 meter at 10 nanometer away from the center of vortex. 5 contour near film is meeting point is 15 nanometer away. 6 contour near meeting point is almost 20 nanometer away. Here is summary of our magnet. We can see from 4 contour layer there exists clear transition. This kind of zero-mass peak splitting point change never been observed in normal superconductor. So this kind of thing should be related to magnetizing mode. Here is summary of our manual. On S-wave superconductor, no matter what kind of magnetic field we apply, this zero-mass peak always starts splitting from center of vortex. Thinner field, same situation. Only on this thick field, and when we apply small magnetic field, this zero-mass peak starts splitting from a distance away. But when we apply a high magnetic field, this splitting starting point goes back to 0. So only in this case we have contribution from magnetizing mode. Then we can do a cutting along 0 NH. We got these 2 lines. Only this low magnetic field case we have a contribution from magnetizing mode. This one we don't have. So we can subtract this one as a background. Then we got this line. This line is the contribution, distribution, spatial distribution of magnetizing mode, but it's only along one direction. So we can rotate this line along y-axis. We got this magic spatial distribution of magnetizing mode. You can see the compare with this calculated result. The agreement is quite good. Also, Patrick Lee and Katie Law proposed this magnetizing mode also has spin and can induce unfavorable reflection. Yeah, everyone knows unfavorable reflection. When we inject an electron to a superconductor to keep the electrons paired in superconductor, we will got a hole back. This is called unfavorable reflection. But when we have magnetizing mode, situation changes. Only when the electron spin is the same as the magnetizing mode, we can got a hole back. The spin of this hole is also the same as the magnetizing mode. So this is called selective equal spin reflection. But if the spin of the electron is opposite to magnetizing mode, this electron cannot induce unfavorable reflection. It will be reflected directly. So they also claim this one can be used to detect the magnetizing mode. Actually, we can use spin polarized STM to do this kind of measurement. When we inject the electron with the same spin of the magnetizing mode as the magnetizing mode, we will got a hole back. We got this low conductance case. But if we inject the electron with the opposite spin, this electron will be reflected directly. We've got a large conductance case. Again, on this thick field at the center of vortex, when tip spin is the same as the applied field, you can see this intensity of zero-mass peak is very strong. But if the spin is opposite, you can see that the intensity is dropped. Same situation when we reverse the applied field. If we move our tip a distance away, we cannot see this spin-dependent phenomena. In our system, we only have topological superconductor and topological insulator and superconductor, no magnetic material. We only apply small magnetic field. So this kind of spin-dependent phenomena can only be explained by spin-selective annular reflection induced by magnetization mode. Yeah, most importantly, all the three evidence we observed appears together and disappears together. When we, on this thick field, when we apply small magnetic field, we can see very strong zero-mass peak. And also we can see this zero-mass peak starts splitting from a distance away. And also we can see this spin-dependent phenomenon. When the magnetic field larger than 0.18 Tesla, its intensity drop, and the splitting starting point goes back to zero, and this spin-dependent phenomena also disappear. So this gives us very strong evidence for magnetization mode. After our the reason is why we can when magnetic field is larger than 0.18 Tesla, we cannot see magnetization mode. The reason is like this: when we increase the magnetic field, the distance between two magnetization mode decrease. When the magnetic field reach to 0.18 Tesla, the distance between two vortexes is only about 100 nanometer. Actually, the size of magnetization mode wave function is about 40 nanometer. So at this distance, the interaction between two magnetization mode is quite strong. So they eliminate each other. Shortly after our work was published, Hong Ling and Hong Yun found this ion-based superconductor are also topological superconductor. This ion-based superconductor has large superconductor gap and low Fermi energy, so they can resolve individual peaks except zero mode and other mode you can see here. And also they can get quantized conductance, so they give more evidence for this magnetization mode in the vortex. Next I will focus on multiple magnetization mode in one vortex. Actually, to make topological quantum computing, we have to study the interaction between magnetization mode. We have to fusion them or braiding them. To do that, we also follow Liang's proposal. We try to make this topological crystal insulator superconducting. This is different from topological insulator. In one unit cell of this topological crystal insulator, they have two or more Dirac-Cohn structure. That means if we make them superconducting in one vortex, we can see two magnetization mode or four magnetization mode. This kind of magnetization mode are protected by crystal mirror, so that they will not impact each other. So we try to grow this tin telluride together with lead, and we found that at a low temperature we got this lateral heterostructure, and at high temperature tin telluride will grow at the top of lead island to get this vertical heterostructure. From this measurement we can see around this line we got this superconducting gaps, and from this measurement we found that this decay length of this proximity effect is really large, larger than 200 nanometers. This is lateral heat transfer case, vertical heat transfer. Same situation along this line. We did this measurement and we found that this superconducting gap almost no change. So this decay length is really long. And with the measurement in the vortex, and we found that in this kind of vortex, for a long distance, this zeros peak then split. You can see from 40 nanometer to 140 nanometer. But in the later case, you can see this zeros peak is split immediately after, when the tip move out of the water center. And we also did the thickness dependent measurement. Here is layer substrate. If we deposit 12 nanometer interval, you cannot see zeros peak. 20 nanometer, you see a little bit. 40, you can see a very strong peak, zeros peak. 80, even stronger zeros peak. Compare with the topological insulated case, when we see this long splitting zeros peak, we can know there exists magnetization mode. And this, as I mentioned before, this magnetization mode should be multiple magnetization mode, and they are protected by mirror symmetry. So we can using a lateral magnetic field to break this kind of mirror symmetry. What we did like this, you can see when we apply a lateral magnetic field 0.02 Tesla, very small one, you can see that this zeros peak started splitting. Increase with this lateral magnetic field, splitting become big and big. But if we apply this lateral magnetic field along the mirror plane, it will not break the mirror. You can see along mirror plane, 110 direction, 0.02 Tesla, low splitting, 0.05 Tesla, low splitting, even 0.08 Tesla, still low splitting. So, here is summary of our measurement. If we apply lateral magnetic field along the mirror plane, we don't break the mirror planes, and this zeros peak then split. But if we apply a lateral magnetic field along other direction, this lateral magnetic field will break the mirror symmetry. Then we can see this zeros peak split immediately. And we asked Jinfeng Jia help us did this simulation. Here is our experiment. When we break the mirror symmetry, zeros peak split, they also got the splitting. If we apply magnetic field along mirror plane, low splitting of this zeros peak. Same result. The simulation and our result is quite good. So this part give very strong evidence for multiple magnetization mode in one vortex. This kind of system give us a very good candidate to study the interaction between magnetization mode. How many minutes do I have?
About 5.
Oh, so I will go through this segmented beaming surface. Actually, for superconductor, when we apply super current, that will create a lot of gap Bogoliubov quasi-particle. This Bogoliubov quasi-particle will induce segmented Fermi surface, since this Bogoliubov quasi-particle only along the supercurrent direction. But this kind of things never been observed. The reason is only in this very small region we can see this kind of segmented Fermi surface. But for most bulk superconductor, this we star and we see it's almost same. So that's the reason why we haven't see this kind of things before. But in our case, in our topological insulator superconductor feature structure, the superconductor gap is induced gap. This gap is small, and topological surface surface state has very large Fermi velocity. So this is what is big. So in our case, we see it becomes smaller. So we give more region to see this kind of segmented Fermi surface. So we prepared this kind of sample, and we found a very uniform area. You can see, and we did this kind of measurement. You can see on the as we see this kind of very good superconductor gap. In the gap, we cannot see anything. Or do QPI, we cannot see anything. Outside the gap, when we do QPI, we can see this 6 branch shape. Then we start applying a lateral magnetic field. This lateral magnetic field will induce a supercurrent along the surface. When we apply very small magnetic field, you can see this gap doesn't touch 0 anymore. That means quasi-particle generate. When we increase the magnetic field, more quasi-particle. Yeah, you can see here along another direction, same situation. And also we can do QPI during the increase magnetic field. You can see along this gamma M direction, we can only see is 2 branch. And if we rotate 120 degrees, we can see another 2. Another 2. If we apply magnetic field along gamma quadrant, we see this 4. This 2 disappear. And this kind of things can only be observed in the gap. When outside the gap, we always see the 6 branch. Only in the gap, we can see this kind of part of this 6 branch. And for S-wave superconductor, no matter what kind of magnetic field we apply, we cannot see this kind of things, no QPIs pattern. And Liang hypothesis with this calculation, our result calculation, you can see the agreement is quite good. And from their simulation, they get this kind of segmented Fermi surface. From this Fermi surface, they can reproduce the QPI pattern. This our result is reproduced or calculated QPI pattern. The agreement is quite good. So our result give first direct evidence for Fermi surface. And this one can also be used to make a new platform for manual both. Here is summary of my talk. This picture structure is good topological superconductor. This system is good for studying interaction between manual mode. And finally, I would thank my polygons. 量数 and Jinfeng class is the theory about these two topics. Finally, I give what is meant. We launched this kind of journal 2 years ago. Welcome to submit your paper to our journal. Thank you very much.
Very nice talk. Are there any questions?
Yeah, so for the case of the Latin satellite system, is there a way to reduce the Fermi energy, make it in closer to the black hole?
Yeah, actually, if we dope something, we can lower Fermi surface, can change the Fermi surface a little bit. Yeah.
Then we can move on to the next talk, which is